In an earlier segment, we saw how the overcurrent relay is commonly used for protection of distribution feeders. However, on high-voltage transmission lines, the preferred method of protection is usually through the application of distance relays, or impedance relays, as they are often called. Why? Well, distance relays are faster, more selective, as selectivity is obtained on the basis of voltage changes as well as current. Easier to coordinate because they are not affected as much by short-circuit magnitude and hence changes in generating capacity and system configuration. The device number for the distance relay is number 21. The earlier types of distance relays worked on the balanced beam principle like this, and certainly this is the easiest way for us to study the concept. The beam is pivoted like a seesaw with voltage and current coils at opposing ends. The voltage coil is fed from the voltage transformer on the line, or more usually on the bus feeding the line, while the current coil is fed from the current transformer on the protected line. Under normal operating conditions, the voltage coil's attractive force is far stronger than that of the current coil. Hence, the balance beam stays in this position. However, if a fault occurs on the line, then the magnitude of current increases greatly, with the result that the current coil now produces much greater attractive force and will overcome the restraint of the voltage coil. The balance beam seesaws in the opposite direction and closes the contacts in the tripping circuit, so tripping the line circuit breaker. The actual point of tripping could be set by adjusting the position of the center pivot, or more simply, by adjusting taps on the voltage and current coils to increase or decrease the number of turns. Either way, the actual point of tripping depends upon the comparison, that is, the ratio of voltage to current, V over I. The relay is in fact measuring the impedance of the circuit being protected, including the load impedance. However, if we have a fault on the line, say a direct phase-to-phase fault, then the circuit impedance to the fault is only that of the conductors themselves, and as we know, this is a relatively small value. Indeed, this is the very reason that the current increases to such a high magnitude. So the relay is set to operate when the measured impedance falls below a specific value. If we know the impedance per mile of the line conductors, we can set the impedance relay to trip for faults within any particular distance from the relay. For example, let's say this line is 125 miles long, and the total impedance is, say, 100 ohms. At the halfway point, the impedance will be 50 ohms, at three-quarter length, 75 ohms, and so on. The relay will be installed at this substation close to the breaker, but it can be adjusted to reach out as far along the line as we wish. Typically, it will be set to protect up to 90% of the length of the line. That is, for an impedance of 90 ohms in this example. Why? Well, relays have a 10% error margin, and we don't want the relay to overreach. The relay is using secondary values from the CTs and VTs, so it really measures secondary impedance. The relay continuously compares voltage and current, and if the primary impedance falls below 90 ohms, it will trip its associated breaker. However, if a fault occurs beyond this line, the impedance will be higher than 90 ohms, and the relay will not trip. So, the relay is giving us the desired selectivity. Usually, a second element is installed to protect the remainder of the line and reach out into the second zone. A third element may be added to reach even further, and so provide backup protection for the first and second zones. In each case, a timer is added so as to delay operation of the second and third elements, in order to allow the primary protection to operate in those zones. It is important to note that we are talking about the impedance that is measured by the relay, not the resistance. Obviously, this is because the conductors contain both resistance and reactance. Typically, the conductors in this 125-mile-long transmission line will contain a resistance of, say, 50 ohms and reactance of 86.6 ohms. Let's plot this on an impedance diagram. Resistance is shown along the horizontal reference vector, and inductive reactance is shown on the vertical axis. Capacitive reactance, if present, would be shown on the negative vertical axis. In this example, we will assume that the quoted 86.6 ohms reactance has taken into account both inductive and capacitive reactance. Plotting resistance and reactance, we find that the total impedance comes to 100 ohms, and it is at an angle of 60 degrees from the reference vector. If we were to set our relay to protect, say, 90% of this line, then the operating point would be here, at 90 ohms. The relay would operate for any impedance along this line between 0 and 90. But that's not all. With the simple balanced beam type relay, it would operate for anywhere within this circle, where 90 ohms is the radius. The balanced beam does not take into account phase angle or direction of current flow. It will trip as long as the measured impedance falls below 90 ohms. In fact, it would trip for a fault upstream, that is, on the bus or on the line feeding the bus. Look, even though current through the CT is reversed, the relay still responds to high current in relation to voltage. That is, it sees a low impedance. On the circle diagram, this operating point would be out here in the third quadrant. To avoid this problem, directional relays, device number 32, are usually combined with balanced beam relays in order to restrict operation to faults downstream of the relay. So this first quadrant is the part of the circle diagram which interests us. We can add to the same diagram the operating circle for the second zone and another for the third zone protection that we mentioned. In each case, the relay element will pick up if impedance falls within its respective circle. For example, a fault out here in the second zone may cause impedance to fall to, say, 140 ohms, which is less than the second element set point of 160 ohms. The relay will operate, and after its timer has timed out, the breaker will trip. But we have not yet considered the impedance of the load. Where does this fit into the picture? Let's take an example. Here we have our same 132 kilovolt line feeding a 90 MVA load on the B bus. That is 76 kV line to neutral and 30 MVA per phase. This gives us a line current of almost 400 amps. Dividing current into voltage, we get 76,000 volts divided by 400 amps equals 190 ohms. This is the impedance of the load. Let's say the load is operating at a power factor of 0.9, that is about 25 degrees lagging. The load impedance can be shown off bus B on the circle diagram like this. But the relay measures the total impedance, that is, the load plus line conductors. So we must add these values vectorially on our circle diagram. We see now that the measured impedance is well outside of the first zone of protection, but it is not far outside of the third zone. So the relay will not operate, and the condition appears to be satisfactory. But on large transmission systems, we often experience load swings. During such a surge, an increase in current could be seen by the relay as a decrease in load impedance, and it may well fall within the third zone of protection. If the surge remained for several seconds, it would cause tripping of the first breaker. Do not forget that our relay for first, second, and third zones is located on bus A. The same thing would happen, of course, if the total load was increased from, say, 90 to 160 MVA. In this case, the impedance may even fall below the setting of the third zone and cause tripping. It is important to remember that where the distance relay is concerned, some consideration must be given to the load characteristics as well as the impedance of the line. Because of these limitations, the balanced beam relay has been superseded by improved types of distance relay, and we'll be looking at these in the next segment. For now, it's time for a break. Please switch off the tape now and go through this material in your workbooks. The Moe relay is typical of the improved type of distance relay. Instead of the beam, this uses a cylinder moving within a magnetic field, similar to the directional overcurrent element. Coils are wound around the electromagnet, and these are fed from the CTs and VTs of the primary circuit. The circuitry is designed to give the relay specific characteristics, as shown by this circle diagram. The relay will operate if the measured impedance from the point of origin falls within this circle. The main feature of this relay is that maximum closing force of the relay occurs when the impedance is at a specific phase angle, usually about 60 degrees. This is similar to the phase angle of the line conductor impedance. The result of this characteristic is that as the impedance phase angle changes, let us say becomes smaller, then the unit will operate only for a lower impedance, that is, a higher level of current. This means that it is less susceptible to incorrect operation due to the load impedance, which can cause the relay's impedance to have a very low phase angle down here. Remember, this unit will only operate for faults within the circle. However, in some cases, we may actually want the relay to operate as a backup for close-in faults upstream. In this case, the characteristic can be offset like this, so that it will operate for very low impedance in the reverse direction. For example, a phase fault upstream but close to the bus would provide a very low impedance and probably fall within the circle here and so trip the breaker. For second zone protection, the second element can be offset like this. Again, because of the relatively narrow band, it is well outside of the load impedance. Phase to ground faults, especially on short lines, provide a particular problem for the distance relay. The arc often contains considerable resistance, so reducing the phase angle of the measured impedance. It also increases the magnitude of the impedance. Consequently, even if the fault is only halfway along the line, the measured impedance often falls outside the operating circle. A common method of getting around this problem is to install relays which measure reactance only. The operating characteristic is shown by this horizontal line. Reactance is measured on the vertical. During normal operation, the total reactance of the load and the transmission line will be above the operating set point. This will be 90% of 86.6 ohms or 78 ohms in our example. If a ground fault occurs halfway along the transmission line, the relay will detect the decrease in value of reactance to 43 ohms and operate the tripping contacts. It will not be affected by resistance in the arc. One problem is that the reactance relay is not directional, and so will operate for faults upstream of the protected zone. This problem is resolved by using the reactance relay in conjunction with a Moe element. The characteristic is shown on this diagram. There are two reactance elements, each protecting first and second zones. The circle diagram for the Mo element shows that it is set to protect the third zone. It includes an external timer to prevent early tripping. But additionally, the Mo element also contains a permissive contact in the operating circuit of the reactance relays. This restricts operation of the reactance relays to this area. The permissive contact will only close when the impedance falls within the circle. If the fault is upstream, the reactance relay will operate. But its tripping circuit will be incomplete because the Mo relay will not have operated and the permissive contacts remain open. Because of this, the Mo unit is often referred to as the starting unit, since it must operate before other units in the relay can trip out the circuit. Distance relays of the solid state type are designed with yet other variations in operating characteristics. Clearly, the impedance type of relay is quite complex and is well developed. It has many desirable characteristics for application on the transmission system, as we shall see in future videotapes. Now, the types that we have been discussing are the most common. If you want further details, you can always refer to our video program on test and calibration of specific relays. An important feature of the distance relay is the provision of zone protection, generally 3 zones. This allows us to provide backup. Generally speaking, the first element protects the primary zone, as shown here, by opening the first breaker, breaker A. The second element provides local backup in case the first element fails to operate. That is, it would trip breaker A after a short time delay. The second element also provides remote backup in the case of a fault on bus B or out on line 2. This would only operate and trip out breaker A in case the primary protection at bus B failed to operate. Similarly, Zone 3 protection is provided as remote backup for faults along the remainder of transmission line 2 and on into line 3. Also, for protection of line 1, a set of distance relays will be installed at bus B looking towards A. The first zone elements overlap, and a fault occurring within this zone would cause the instantaneous operation of both relays and the opening of both breakers. Now, for a fault in the last 10% of line 1, breaker B trips instantaneously, but we would have to wait for zone 2 clearing at A. Remember, remote backup will isolate a greater part of the system and perhaps cause outage to a greater number of customers. Also, there may be more damage and system shock. In this context, intertripping using various communication channels could be used. We'll discuss this in future tapes. Nowadays, more emphasis is being placed on local backup. Several types of protection are provided for each zone, and frequently a duplicate, so-called redundant installation of identical relays is provided. This would be fed by separate CTs and a separate source of DC tripping current. This in turn will be fed to separate tripping coils within the breakers. Usually in a fault condition, both of these protection circuits will operate in parallel at the same time. We will be looking in more detail at backup and the application and operation of distance relays in future tapes. In this videotape, we've tried to survey the main features of the most common types of protection relay. Of course, there are other types of relays, such as frequency relays, negative phase sequence relays, as well as many others which we have yet to discuss. But don't worry, we'll get to these in due course. Now that we have a good understanding of how relays work, we'll be looking at some of the basic technology of protection in the next tape. before moving on to study specific applications. For now, please switch off the videotape and very thoroughly go through this material in your